Welcome to the course on metal additive manufacturing. We will now discuss in this small lecture exclusively on various phase diagrams. I repeat, it is a small lecture, maybe for 20 minutes or 15 minutes. This exclusively covers like the different phases which can happen in alloys. This diagram or this information is very much required, because if you are going to talk about all these alpha phase, beta phase, gamma phase, martensite, austenite in the microstructure, all these things can be derived from these diagrams, and this diagram will dictate the microstructure, in turn describes or defines the service condition of the part in real time. In this lecture, we will try to cover the phase diagram of iron carbide diagram, aluminium alloy, titanium alloy and nickel alloy. Whatever four we are trying to cover, we have picked up the alloy composition which is exhaustively used in metal additive manufacturing. First, we will look into iron carbide diagram. Iron carbide diagram is very famous and it is very common. People, when they teach in your basic material science course, they try to go through this phase diagram. So, this phase diagram is all about taking two metals, one is ferrous, the other one is carbon. These two are getting mixed to each other. When they mix at varying compositions and at varying temperature, what will be the microstructure? This will be our prime focus. So, if you try to look into it, you have here 0 carbon, and maximum carbon in cast iron can happen when C gets diffused into iron, we can go up to 6.7%. Anything above 6.7, it does not form a proper alloy. So, and it is not having engineering properties. So, we will always look forward for iron carbide diagram where the carbon content is maximum up to 6.7. But when we are looking at the additive manufacturing, we always work in a composition close to 2.1 or 2.2. This is where is the domain we will start working. And cast iron is predominantly used for casting and for bulk material formation or bulk part formation, we use cast iron. So, let us focus only in this zone where it is talking about 2.1 or 2, this zone we are trying to talk about. So, in this zone you can see here, you can get hyper-eutectoid condition and hyper-eutectoid condition. So, it is hypo-eutectoid and the next one is hyper-eutectoid. If I try to take the composition of mixing of iron and carbon and take it to very high temperature up to 1400, 1500, which is very common when you are trying to use in additive manufacturing, when you are exposing it with respect to laser or with electron beam. The temperatures can go very high, easily it can go up to 1000, and if you slightly push it further, it can go up to 1500, 600. So, you are almost in this zone. So, when you are at this zone, you see it is completely liquid. Now, from here, if I slowly start cooling it down, you see here I get into gamma plus liquid phase. Then when I push it further down, I get into austenitic phase. So, what is austenitic phase? You see this is what is the microstructure it looks like. You will have grain boundary, and then you will have gamma, which is quite common. Now, I further allow it down to go to this temperature. You can see here there are small precipitations of carbon which are getting trapped or formed along the grain boundary. So, these trapped ones are called as iron carbides, and you can see the gamma there. When I further go down, with this ferrous carbide Fe3C, which was formed along the grain boundary, which was got precipitated or formed along the grain boundary, it will try to get spread all around and you try to get a pearlitic phase. So, you just brought down the temperature, you see how many different phases are coming. Now, in all these phases, suppose let us assume I pause the temperature and then I quench it down. Then in my quenched sample, predominantly I will be able to get the microstructure from where I paused and I quenched. So, when I do with iron carbide diagram and with laser as a source for heating, these microstructures are very common to tailor make it. So, when I go further down, you get this pearlitic structure. You can see here the tectoid solution and peritectoid, this thing forming in the microstructure. So, now here I have a combination of pearlite and cementite. So, maybe pearlite and cementite might give a good mechanical properties, maybe. I am just giving you an example, maybe, or it can give you good toughness. So, now what do? I try to get this microstructure and I freeze it. Anything less than 600, 700 degrees Celsius or somewhere close to 700 degrees Celsius, whatever you get is frozen up to room temperature. Now, you try to quench it and get it, or from the above you try to quench it and get it, you get the desired microstructure in the workpiece. In the same way, when I try to do it somewhere around about here, you can see here in the austenitic phase, you have this gamma phase which is there. So, here and here it is the same. The only difference between this and this is the compositional difference of C which is getting pushed inside the ion or in the microstructure. Then I move it to the next phase. So, this phase you have got Fe3C, and here whatever is getting here done, and here it will be almost the same. When I further push it down, I try to get this structure all around the material. When I go further closer, that means to say I reduce carbon to a large extent and I drop it down from 900 degrees, I go down, I get a gamma phase, then I get the precipitation. Here you said alpha plus gamma. What is gamma? This is gamma. What is alpha? Alpha is a phase which is predominantly seen here, which is nothing but a ferrite phase. So, you can see here alpha plus gamma. So, you see alpha plus gamma which is there. Then further I move down, you see that this gamma whatever is there, it is getting spread along the grain boundary nicely. I get it above somewhere around about 800 degrees Celsius or somewhere around about 723 degrees Celsius, I get this. So, now I further move down, you see here there is a pearlitic phase, there is Fe3C, there is a eutectoid alpha, and then it is protectoid alpha you get. So, all these things are getting. So, now these things try to dictate the microstructure and the ductility of the component. A1, the upper limit of ferrite cementite phase field. So, you can see A1 is here. So, you can get a field here, right, A1. Then A2 is somewhere here, the temperature where iron loses its magnetism property, so called Curie point can happen at A2. At A3, you try to have the boundaries between gamma austenite and the austenite ferrite field you try to get. A4, you get the point in this case where alpha changes to delta, you get here. Then we have ACM critical is a point here, which the boundaries between the gamma austenite and the austenite cementite field you can try to get this. So, from this diagram you can try to see how carbon and iron gets influenced with each other, and you get varying microstructures at varying temperatures. So, you can see this and then you can see this in turn will be affected by your residual stress which it is getting introduced in the additive manufacturing. Next, when we move into aluminium alloy phase, So, you can see weight of nickel percentage is given here. So, you have temperature, you have atomic percentage of nickel. So, this is used for aluminium and nickel getting fixed. So, this side is nickel and this side is aluminium. I have just taken as an example of one particular alloy. So, here you can see it is liquid phase, and as and when I start moving down, you can see here what are all the different compounds or compounds which are getting formed. Al3Ni is getting formed, Al3N2 is getting formed, Alni is getting formed. So, you can see all these things, each one has its influence on the output. Depending upon the composition, what you have mixed it in the powder bed fusion or in directed energy deposition, you try to mix that alloy in the starting material itself, and when we expose it to laser, you see it undergoes to various temperatures. Depending upon the temperatures, various phases gets formed. So, if you are able to maintain at around about 65% of nickel at around about 700 degrees Celsius, you try to get these compounds getting formed. So, just by changing the composition, you can get multiple microstructures in one component. When we are looking at titanium alloy, it is titanium alloy, you can see Ti6Alv4 is the most common one which is used. So, you can see here when we are trying to change the aluminium composition with respect to titanium, let us assume it is dropping down somewhere here. So, you will see here first it is at a liquid phase, then from here it enters into a beta phase, beta 0. Beta 0 is nothing but beta titanium alloy, then it moves into alpha where alpha titanium is there. From there you can try to get alpha titanium to 0.4. When you slightly shift, this gets into alpha 2, which is nothing but Ti3Al. Okay. So, when I get into this portion, gamma I try to take is TiAl, when I try to take zeta it is TiAl3. So, you get different compositions at proportions whatever you mix and make an alloy, and then you try to see their phase diagram when you try to find out the multiple phases which are getting formed. When we talk about nickel alloy is pretty interesting. It is nowadays used in aerospace application. You see at around about 220 Kelvin, you find it as a liquid. I drop down. Okay. So, you can see here at one page it is nickel. So, I drop down and then I get into beta phase. Okay. So, this beta phase is different as compared to that of your gamma, gamma prime. So, they are different. So, here you will get this Ti3Ni which is forming here, and you have Al3Ni, Al3Ni3, Ni5 will be formed here, and at this point you get gamma double prime. So, high pressure solidification process produces gray, white and black phases, but here we do not use high pressure, but without doing high pressure, high temperature and instant cooling, you can get multiple combinations. Ai3Ni is gray, alpha aluminium is black and Al3Ni is white. So, depending upon the microstructure, you can easily find out by looking at the microstructure. If it is gray, it is Al3Ni, if it is alpha Al is black, Al3Ni2 is white. So, when the peritectic reactions cannot be carried out due to primary phase incapability to touch the liquid phase, the growth of the peritectic phase can only be achieved through solid phase diffusion. So, what is the mechanism it undergoes, that is a separate course of itself, but we are only trying to understand the influence of laser, its parameters with respect to forming of these phases. In the same way, electron beam, its parameters. So, what undergoes the growth of the peritectic phase can only be achieved through solid phase diffusion, and direct solidification from the undercooled liquid phase it can happen. So, nickel, you try to get all these combinations to meet out to the requirements. When you look at nickel alloy phase diagram, you can see hypo-eutectic. So, this is eutectic phase which is alpha Al is there. So, here hypoeutectic, the aluminum composition is close to 96% and the nickel is 4. Eutectic is 94, 6 is the nickel percent, and hypereutectic is 91 and it is approximately 8. So, if you see hypoeutectic, this is how the microstructure looks like. When you look at eutectic, it is looking like this, and when you look at hypereutectic, these are Al3Ni white phases which are present, and it is eutectic phase. So, in this lecture, I have few assignments for you. One is try to look for Ti6Al4V. So, try to look at this alloy and try to get its microstructure. At various temperatures. Okay. Next, try to see some literature on Ti6Al4V where they have quenched the alloy from very high temperature. We are talking about 800 degrees Celsius to RT, room temperature. See the alloy microstructure. Next one, you try to look at inconel 718, which is exhaustively used for aerospace application. Same thing whatever I have written. So, one is microstructure, varying microstructure, structure at varying temperatures versus temperature. Then you try to see a quench cycle. Then the third one is going to be Ti6, then it is going to be Aluminium 6XXX series. Try to do the same microstructure, versus temperature, and then with quenching cycle. So, when you try to look into all those things, it will try to give you a wider perspective and you will see varying microstructures are getting formed. So, that will try to give you an understanding of the microstructure and its influence. Microstructure and its influence on mechanical behavior. You can see that. Thank you very much.